One of the main concerns of someone who is involved in machine learning is data. When dealing with a limited number of features, it becomes crucial to focus on effective data preprocessing methods to enhance classifier performance. Let's look at ways to improve classifier metrics when the number of features is small. In the absence of additional factors, the quality of the classifier can be improved by ensuring monotonicity of the target variable from the features. Additionally, expanding the feature space by increasing its order can also contribute to improving classifier accuracy. Now, we will analyze a real dataset consisting of order data from a café. Our goal is to determine the delivery status of orders based on two attributes: the time they were placed and the time they were delivered. The dataset comprises order information from a single day at a café specializing in ready-to-eat food deliveries to customers. To begin with, let's import data from the file. Order time column is not convenient from the point of view of mathematical analysis and visualization, so it is necessary to convert the data to another form. Let's create the new feature, which will contain information about the time of order placement in seconds. In order to determine any irregularities, let's draw graphs and interpret them. From the diagram we see that, on average, the office is delivered faster. Most likely the café premises are located closer to offices than to residential neighborhoods. We can also see that the longer the delivery time, the fewer orders the café receives. Now we can see that by the time the order is placed, the proportion of class overlap is really not high. We can observe 3 significant spikes in orders during the lunch hour, for customers opting to have dinner at home instead of cooking, and for those in the office working continuous production shifts. Firstly, we will import the necessary tools for building the classifier. Use this function to split the sample into training and test samples. The parameter test size indicates the proportion of the test sample. Additionally, the standard scalar function will reduce the feature values to the standard form, where u is the mean value and s is the standard deviation. After that, we create the classifier using logistic regression. The coefficients of the logistic regression equation are found on the training sample. Then the found equation is used to predict the class of the object on the test sample. Also, to analyze the obtained result, let's write the special function. By double-checking, we verified that the model is not overtrained and shows not bad quality. All metrics on the total training sample are 0.88, on the test sample 0.91. Is it possible to improve the obtained solution? To answer this question, let us first look at the graphs again. On the graphs we see the same area where representatives of the same class are predicted incorrectly on both training and test samples. Let's try to fix it. We need to write the function which order time in seconds column shift the time of all orders cyclically to the left, closer to the beginning of the day. We improved the quality of the classifier by ensuring monotonicity of the target variable from the features. The rules are now satisfied as the time of order arrival increases. The probability of home delivery also increases similarly, as the time of delivery increases. The probability of home delivery also increases. Unfortunately, it is not always possible to ensure monotonicity of the target variable from the attributes without using any additional tools. Is there any other way to improve the quality of the classifier? This is not only possible, but also necessary. One way to improve the classifier is to increase the order of the feature space. For example, if it is hard enough to draw lines separating classes in a plane, you can already find a plane in 3-dimensional space that will do it better. All time points need to be transformed using sine and cosine. Transformations are done according to the following formulas here. X represents the value of the time point, and K represents the value of the time period in units of time points. For example, if time points are measured in seconds and the time period is 1 day, then K is equal to 86,400, or if time points are measured in days and the time period is 1 week, then K equals 7. Now, let's build a classifier again on the transformed data. As we see, we improved the quality of the classifier by increasing the order of the feature space. The results of the last classifier on the test sample turned out to be the highest. Today, our meeting comes to an end. Thanks for watching the video. We appreciate your time and interest. Stay tuned for more insights on machine learning in our upcoming videos. See you later.